Alright, let's move on to Quicksort. So Quicksort is a very conceptually difficult sort to get in, conceptually get sometimes, but it's a very easy to code sort. So let's go through an example first, and then we'll come back and analyze it a little bit. So I know these numbers are a little hard to see because they're kind of tiny, so I could do so much on the board, but I'll name everything off. So here in our example from the book, 9, 20, 6, 10, 14, 8, 60, and 11. And what we're going to do is sort this. Now the first important thing about Quicksort is you have to determine a pivot. And we're going to talk a little bit more about how you might determine a pivot after I go through the example. But for starters, let me just explain what the pivot is. The pivot is quite literally a point which you pivot around. And that's why they call it the pivot. So the idea of the pivot is you pick a point in the array, whatever data structure you're using to represent this, but we're just going to call it an array for starters for now. And you try to find the elements that are on the wrong side of the pivot on both sides, and you flip them. So the idea is you pivot the items around the pivot so they're in the right spot. And that's exactly how the algorithm works. In fact, it should just be called pivot sort for that reason. So we're going to arbitrarily for now choose a pivot to be the middle element. And so the pivot will be 10 for the start. I've written that there. So now what we do is we take pointers from both sides, and this is a very kind of graphically physical motion to explain this, and you keep going until you find numbers that are on the wrong side of the pivot, which is for the left side, numbers that are greater than or equal to the pivot, and on the right side, less than or equal to the pivot. So first we look at 9. 9 is less than or equal, or is not greater than or equal to 10, the pivot, so we leave that alone, and we move on to the next item, 20. 20 is greater than or equal to 10. So this, we stop here for now. And now we go from the right side. And first we look at 11. Is 11 less than or equal to 10? No, it's not. So we move. Is 60 less than or equal to 10? No. So we move over. Is 8 less than or equal to 10? Yes. So we stop here. Now what we do is we have 2 points marked around the pivot. And we flip them. So coming down now, we have 8 and 20 flipped there. And now we continue by taking the next item on both sides, because we've already looked at these items, so we do +1. So we look at the 6 and the 14 now, and we continue. Is 6 greater than or equal to the pivot point of 10? No. So we move over. Is 10 greater than or equal to? Yes. So we move over, so we are done. And on 14, is 14 less than or equal to? No. So we keep moving, and 10, yes it is, so we're done. And now we stopped at the pivot point here on both sides. And now what we do is we recurse down. So we divide the array into the point at which each side stopped. So the left side stopped at the pivot point from 9 to 9, 8, 6, 10, the 0 through 4 array position. And the right side pivot point stopped at the 10 as well. So we move up 1 since we can only take half the array. 14, 20, 60, 11. And then we take the recursive call on each side. Okay, so now we've recursed, and we have 9, 8, 6, 10, 14, 20, 60, 11 on that side. So we're just going to take left side. And now we do the same thing. Since it's a recursive function we talked about last week, what we're going to do is we're going to apply the same method, but to a smaller problem. So now we have half the array. And we need to determine a pivot point. Again, we're just going to pick the element in the middle, which is the middle minus 1 in this case, because you can't have a middle in a 4-element array. So we're going to pick 8. So now our pivot's 8, and now we do the same thing. So is 9 greater than or equal to 8? Yes, it is. We stop there. On the right side is 10 less than or equal to 8. No, it's not. So it's on the right. It's fine the way it is. We move on. Is 6 less than or equal to 8? Yes, it is. So we stop there. And now we take these 2 points and we flip them. And now we got 6, 8, 9, 10. And now we're going to continue. And I'm going to kind of move faster now that we understand the basic moving to flip points, and just kind of go through this a little bit quicker. So we're going to, then the next iteration, both will stop at 8, because as you can see, it's a sorted array. And you can convince yourself that in a sorted array, they stop at the right spot. And now we have 6, 8, 9, 10. Now we're going to do the same thing again. We're going to recurse, because the program doesn't know at this point that this is sorted correctly. So we recurse again, 6, 8, and 9, 10. So now 6, 8, very quickly, because the pivot will be 6, because it's half minus 1 again. And now nothing will need to be flipped. And of course, there's only 2 elements, so only one loop iteration will run, and it'll be done, and it'll be fine. And that's it. So now that we're done with that, we basically have these 2 array positions sorted. And now the same thing happens over here, and you'll see nothing needs to be flipped. So this whole side is sorted. Okay. Now, what we have here is 14, 11, 60, and 20. And I'm sorry, up here. Now, what we need to do is apply the same thing, and again, I'm going to move a little faster. So we move this way and this way until we find the wrong numbers around the pivot of 20. We'll stop at 20 here and 11 there, flip them, 14, 11, 60, 20. Now we do the same thing again, we'll stop at 60 and 20, flip them, 14, 11, 20, 60, and now we'll both stop at 20. Now notice the pivot moved around a little bit here. The pivot doesn't have to stay put just because it's a pivot value. It can actually move to wherever the appropriate array position is, otherwise it would never really get sorted. Okay, once we've reached this point, now we recurse, and since we're using the convention of 1 plus the point at which things stop on the left-hand side of the recursion and then the rest on the right, then this actually comes out to be broken up into a 3-element array this time and a 1 element. So coming over to this side here, so we break this into 14, 11, 20, and then 60. Now this is a base case, right? So this is fine the way it is, and it's done. And it's in the right sorted position, so that's good. 14, 11, 20 now needs to be sorted. So again, we apply the pointers and move them over. Our pivot's going to be the middle point again, which is 11. So 14 is on the wrong side, so we stop there. 20 is fine. 11 is the pivot, it's equal to, so we stop there, and we flip. 11, 14, 20. And now, moving both pointers over, we'll stop at 11, which means we're done. And now we recurse again to 11 and 14, 20. And then, obviously, this will sort quickly, 14, 20, the same way as before, and we're done. And you see when you put this all together, 6, 8, 9, 10, 11, 14, 20, 60, aha, it is sorted. So, Quicksort really works. I wasn't lying to you. Now let's talk about the complexity here. So, without going too far into the mathematics, again, glazing over some stuff, what's happening is in the average case, the problem's being broken down into smaller pieces by about a half or so. So if we choose the pivot correctly, then that means the left and the right-hand side arrays will come out to be half. And then what we're doing is we're having the problem each time, and when we do that, we have a log n factor. And each time we have to look through the whole array still, so we're O of n and searching through the array to move and pivot, but only log of n times we're doing that in a good case. So this is an n log n sort in the average case, the most of the time case usually. But it's actually O of n squared in the worst case. And what happens there is the pivot, if your pivot is poorly chosen to be one of the border elements, the largest element or the smallest element, then what will happen is, like if it's 60 in this first iteration, then the 60 will get put in the right spot, but the start and end pointers that move over will end on the very last spot. And then what happens is you're recursing over all but 1 element and 1 element. And so you end up not splitting the problem by half anymore, you end up splitting it by only taking 1 element off. And when you do that, you're basically creating an O of n times O of n, or yes, O of n minus 1, n minus 2 multiplied out. And that comes out to the same as the other sorting algorithms we talked about, n squared. And that's no good. And when does that happen? That happens when you pick a bad pivot, because you pick the first item in a sorted array, perhaps, or you've just gotten unlucky. Now, gotten unlucky is a random problem that's going to happen. But it's not so bad if once in a while, perhaps, the sort is O of n squared, but most of the time it's log of n. That's something to think about because it's a very quick and easy implemented sort, which is why it's called Quicksort. So it has that advantage. Also doesn't use any additional space. You don't have to change or add some kind of array, you just flip things around. And so you're using recursion space, so you are using log of n space, but you're not using a massive amount of space like you would in some other algorithms we're going to talk about. So to choose a pivot wisely is very important. So what you want to do is you want to pick a good pivot that's somewhere in the middle of the values. And you can do this kind of easily by taking a median, by doing some quick preprocessing to determine a value that's not at a border case. And there's lots of different methods to do this. The book talks about them. I encourage you to do some web research. And what you'll end up with then is a good algorithm that on average, or 99% of the time, will be O log of n. And that's a really good sorting algorithm.